Welcome back to the deep dive. Usually when we sit down to record one of these, we have a very specific target. We take a stack of articles about a new AI model or, a historical battle or maybe a psychological bias, and we get the microscope out.
Right.
We zoom in until we can see the cracks in the pavement.
We obsess over the details. I mean, that is the brand.
Exactly. But today,
Yeah.
today we are doing the exact opposite. I was looking through the research packet you sent over, and I realized we aren't zooming in at all.
No.
We are zooming out, and not just a little bit. We are zooming out as far as it is physically possible to go.
We are viewing the whole board today, the whole playing field.
We aren't looking at a star or a planet or even a galaxy. We are looking at the whole enchilada. We are talking about the biography of the universe.
The entire story.
From the very first fraction of a second all the way to the absolute end of time.
It is a bold ambition for 1 hour, I'll admit. But what I love about the sources we have gathered for this deep dive is that they frame the universe in a way that feels very personal.
It does, yeah.
They treat the universe almost like a living character. It has a birth, it has a messy, chaotic childhood, it has a prime of life, which, spoiler alert, is where we are right now.
Right now.
And eventually, like everything else, it has a decline into old age and death.
It's the cosmic perspective. And I have to say, when you really try to hold that perspective in your head, it messes with you.
It absolutely does.
I was reading through the notes on the scale of this biography, and there's this classic analogy that always floors me, the 24-hour clock.
It is the absolute best way to ground yourself. Because if I say 13.8 billion years, that is just noise. The human brain cannot process a number that big.
Just a word.
It just sounds like a long time, but we all understand a day. We know what a morning feels like. We know what a lunch break feels like.
So for everyone listening, I want you to visualize a clock, a standard analog clock on the wall. We're going to take the entire history of the universe, every moment from the Big Bang to right now, and squeeze it into a single 24-hour cycle. The Big Bang happens exactly at midnight. 0000.
The clock starts ticking. The story begins.
Now, here is where my intuition fails me every time. I assume that things happen pretty quickly. Midnight is the explosion. Maybe the stars show up at 12:30. Maybe the Earth forms around breakfast time.
That is how we usually tell the story, right? We skip the boring parts. We jump from highlight to highlight.
Yep.
But on this scale, the boring parts are most of the day.
It is agonizingly slow. In this analogy, the Earth, our home, doesn't even form until 4:00 p.m.
Just think about that for a second. The sun comes up, people go to work, they have lunch, the afternoon slump hits, and for all of that time, there is no Earth.
None.
There is no solar system. The day is 2/3 over before our planet is even a concept.
That really highlights how much cosmic history happened before we were even a possibility. But then you zoom in on life. You'd think, okay, Earth is here at 4:00 p.m., so maybe dinosaurs are around dinner time.
Not even close. Not even in the same ballpark.
The dinosaurs.
Yeah.
The absolute icons of ancient history. They don't show up until 11:41 p.m.
They get a 19-minute run. That's the whole empire, the Jurassic period, all of it.
And then, whack, the asteroid hits at 11:57 p.m.
They're gone, just like that.
And we're left with 3 minutes on the clock.
And that is where we come in, the very, very end of the day.
Human history. I don't just mean iPhones and podcasts. I mean everything. The first time a human looked at a fire.
The cave paintings.
The pyramids. The Roman Empire. Shakespeare. World War II. All of it.
The entire human drama. Every war, every poem, every discovery.
It all occupies the last second. 11:59 p.m.
It gives you a very specific feeling, doesn't it?
It makes me feel like an uninvited guest. Like we arrived at a massive party just as the lights are coming on and the janitors are sweeping up the confetti.
Laughing, that's a great way to put it.
We missed the appetizers.
Yeah.
We missed the main course. We missed the wild dancing. We just walked in the door.
That is a valid feeling.
Yeah.
We are late to the party. And this is the mission of today's deep dive and why I think this topic is so empowering. Even though we arrived late, we found the receipts.
Found the receipts. I like that.
We did. Through physics, through astronomy, through mathematics, we have managed to reconstruct the timeline of the party we missed.
We're cosmic detectives.
Exactly. We know what happened at 12:01 a.m. We know who was dancing at 6:00 a.m. And that is what we are going to do today. We are going to walk through those receipts. We are going to reconstruct the biography of the universe, starting from the breakdown of physics at the start, all the way to the frozen silence of the deep future.
So let's go back to midnight. Section 1, the first breath.
T = 0. The Big Bang.
And immediately we have to tackle the elephant in the room. The question I think every single person asks when they first hear about the Big Bang. I know I annoyed my science teacher with this one.
We all did.
The Big Bang started everything. But what was before the Big Bang?
It is the most natural question in the world, is how our brains are wired. We are creatures of cause and effect.
Right. If a bomb goes off, someone must have lit the fuse. If the universe exploded, something must have happened 5 minutes earlier to cause it.
Exactly. Was there another universe? Was it just a black void waiting to be filled?
Yeah.
I was there.
Here is where the experts tell us we have to stop thinking in human terms. According to general relativity, that question doesn't actually make sense.
What do you mean?
It isn't just that we don't know the answer, it's that the question is broken. The premise is wrong.
How can the question be broken? It feels like a perfectly normal question.
Let me give you an analogy that Stephen Hawking used. It's the best one I've ever heard for this. Imagine you were standing on the Earth. You start walking north.
Go.
You walk past New York, you walk past Canada, you cross the Arctic ice. Eventually you reach the North Pole.
Okay, I'm standing on the pole, the geographic North Pole.
Now, take one step north.
I can't. If I take a step, any step, in any direction, I'm moving south.
Exactly. There is no such thing as north of the North Pole. It isn't because there is a wall there or because we haven't explored it yet.
It's a geometric impossibility.
It's because the geometry of the Earth makes the question meaningless. North originates at that point.
I see where you were going. This is a bit of a mind bender.
The Big Bang is the North Pole of time. It isn't just an explosion in space. It is the origin of space and the origin of time itself.
So there's no before, because the time coordinate simply does not exist past that point.
It's like asking what's on the other side of the first page of the book. There is no other side. That's where the story starts.
That is frustratingly logical. It's like hitting a wall in a video game where the map just ends.
T=0 is the ultimate wall. But we can get incredibly close to it. We can't see the moment itself, but we can theorize back to the Planck epoch.
The Planck epoch. Okay, so this is the tiniest fraction of time imaginable.
It is 10 to the power of negative 43 seconds after the Big Bang. I want you to just picture that for a second. That is a decimal point, 42 zeros, and a 1.
A sliver of time so small that physics as we know it barely applies. The rules just break down.
At that moment, the entire universe, everything we see today, billions of galaxies, was squashed into a space smaller than a single atom. And it was hot, incomprehensibly hot, a temperature with 32 zeros after it.
And it's just energy. What was it made of?
Pure, unified energy. The 4 fundamental forces of nature that we know today, gravity, electromagnetism, and the 2 nuclear forces,
The strong and weak force.
they were all melted together into one super force. It was a knot of perfect unity, of perfect symmetry.
And then the knot unravels, and we get the growth spurt. Inflation.
Inflation, this is a crucial chapter in the biography. It's maybe the most important thing that happened in that first second. Between 10 to the power of negative 36 and 10 to the power of negative 32 seconds, the universe expanded.
But expanded is too weak a word. It really is.
Exploded outward. It was a change of scale so violent it's hard to describe.
How much expansion are we talking about here?
It grew by a factor of at least 10 to the power of 26, at a minimum.
Okay, I need a visual for that. Those numbers are they're just numbers.
The source material uses this one, and it's perfect. Imagine a grain of sand, a single tiny grain of silica.
Got it.
Now imagine that grain of sand growing to the size of the entire observable universe, everything we can see with our best telescopes, in less than a billionth of a trillionth of a trillionth of a second.
Wait, hold on. I have to stop you there. Because that sounds illegal.
Laugh is illegal by whose laws?
Einstein's laws.
Yeah.
Nothing can travel faster than the speed of light. If a grain of sand becomes the size of the universe that quickly, the edges are moving way, way faster than light speed.
You have spotted the apparent paradox. And you are right. Nothing can move through space faster than light. You can't build a rocket and race a photon. You lose.
Right. So what gives?
But this rule has a loophole, a very important one.
There's always a loophole.
The rule applies to objects moving through space. It does not apply to space itself. Space is the canvas. The canvas can stretch as fast as it wants.
Oh, I see. So the speed limit is for the cars, not the road.
Precisely. During inflation, the road stretched out instantly, carrying everything with it. The galaxies aren't flying through space. Space is growing between them, pushing them apart.
But why? Why did the universe need to do this insane magic trick? Why couldn't it just expand slowly and politely? What problem does this solve?
It solves the smoothness problem. The reason the universe today is so uniform.
Smooth. Have you seen the Rockies? It feels pretty clumpy to me. We have planets and stars and voids.
Locally, sure. But if you look at the big picture, the cosmic microwave background, that baby photo we'll talk about, the temperature of the universe is almost exactly the same in every direction.
Okay.
If you look deep to the left and deep to the right, to patches of sky that have never been in contact with each other, the background heat is identical to 1 part in 100,000.
Why is that weird? Why shouldn't it be the same?
Imagine you have a cup of coffee on one side of a football stadium and a cup of tea on the other side. You measure them, and they are the exact same temperature, down to the millionth of a degree.
That would be a huge coincidence.
It shouldn't happen. They are too far apart to have influenced each other, to have shared their heat. The only way they could be the same temperature is if they were touching a split second ago and then someone moved them apart faster than they could cool down.
Ah, so inflation explains why the universe matches itself. It took a tiny, uniform spot and stretched it out before it had time to get messy.
Exactly. It stretched the wrinkled sheet flat, but, and here is where it gets really interesting, it didn't smooth it out perfectly.
And thank goodness for that. A perfectly smooth universe would be a boring one.
It would be a dead one.
Right.
There were tiny, microscopic jitters, quantum fluctuations, little ripples of energy in the subatomic world. Inflation took those tiny ripples and stretched them across the cosmos.
So the reason we had galaxies today, the reason matter clumped together to form stars and planets and, well, us, is because of those tiny quantum jitters getting stretched out during inflation.
Yes, every large structure you see in the universe, every galaxy supercluster, started as a subatomic flicker in that first instant.
So if you look at a galaxy, you are essentially looking at a fossilized quantum fluctuation from the first fraction of a second of time.
You're looking at magnified quantum noise. It's an incredible thought. Our DNA is a consequence of that noise.
That is wild. Okay, so inflation ends. The universe is huge now, but it's still a hot soup. This brings us to the primordial soup phase and the first great drama of the universe. The notes call this the cosmic massacre.
Baryogenesis. This is the mystery of why we exist at all. It's the reason there's anything here to talk about.
Because matter has an enemy, an evil twin.
Antimatter. For every particle of matter, like a proton or an electron, there is a mirror twin. An antiproton, a positron.
Same mass, but opposite charge.
Right, and they are mortal enemies. If matter touches antimatter, poof,
Total annihilation. They just ban.
they turn back into pure energy. Now, symmetry, the laws of physics as we understand them, would suggest that the Big Bang should have produced equal amounts of matter and antimatter, 50-50.
And if that had happened, if it was perfectly balanced,
They would have all found each other in that hot, dense soup, shook hands and annihilated. The universe would be nothing but light.
so no stars, no gas, no planets, no...
Just a bath of radiation, a very thin, very cold, very empty universe.
But clearly that didn't happen. Because I'm sitting here talking to you and I'm made of matter.
Exactly. Something tipped the scales. We still don't fully understand why. It's one of the biggest mysteries in physics. But for every 1 billion particles of antimatter, the universe created 1 billion and 1 particles of matter.
That's the margin of victory, 1 in a billion.
That tiny imbalance was enough. The billion pairs annihilated each other in a massive flash of energy, which, by the way, is still flying around the universe today as part of the background radiation.
But that one single leftover particle, that survivor,
The Lone Ranger.
that's everything.
That survivor is what makes up all the matter we see today. Every star in the sky, every galaxy, the Earth, the water in your glass, the atoms in your brain, they are all the leftovers from that massacre.
We are the 1 in a billion that didn't get canceled out.
Literally. We are the rounding error in the cosmic equation.
So the massacre ends, the antimatter is gone, and we are left with this hot, expanding cloud of matter. This brings us to section 2, the Dark Ages and the first light.
So now we are a few minutes into the life of the universe. It has cooled down a bit, but it is still incredibly hot. A few 100 million degrees. It's a plasma.
A soup of protons and electrons, not yet atoms. And the notes describe this era as the fog of war.
That's a good visual, because that's what it was like. Imagine being inside a thick, glowing orange fog. Visibility is 0.
Why? If there's light, if it's glowing, why can't I see anything?
Because the light is trapped. At this point, it is too hot for atoms to form. Electrons are flying around freely,
They haven't been captured by protons yet.
and free electrons are really, really good at blocking light. They act like goalies. A photon of light tries to move, and wham, it hits an electron. It bounces off, tries to move again. Wham, hits another one.
It's a pinball machine. The photons can't go anywhere?
It's a prison for light. Light cannot travel in a straight line for more than a few millimeters. So even though the universe is glowing, it's opaque. You couldn't see your hand in front of your face.
And this lasts for a long time. It's not a quick phase.
No, this goes on for 380,000 years.
380,000 years of glowing fog. And then something snaps. The recombination event.
The universe keeps expanding. As it expands, it cools. Finally, it hits a critical temperature. 3,000 Kelvin. That is the magic number.
About the surface temperature of a cool red star.
Exactly. And suddenly, it is cool enough for protons to grab those wild electrons and hold on to them.
They form the first atoms.
Neutral atoms.
Hydrogen, mostly, a little bit of helium. And because the electrons are now locked up in atoms, they aren't blocking the light anymore. The goalies are off the field, the fog lifts.
Instantly.
All at once, across the entire cosmos.
And all that trapped light, all those photons that have been bouncing around for 380,000 years.
They fly free. They stream across the universe in straight lines for the first time ever. And this is the cool part. We can still see that light today, right? This isn't just theory.
We can. It's called the Cosmic Microwave Background, the CMB. That light has been traveling for 13.8 billion years. It has been stretched out by the expansion of the universe, so it's not orange light anymore, it's microwave radiation. But it is there.
It's the oldest picture we will ever take.
I read somewhere that if you have an old TV, the boxy kind with the bunny ears, and you tune it to a dead channel,
The static, yeah.
about 1% of that static, the snow on the screen, is actually that ancient light hitting the antenna.
You are watching the baby photo of the universe.
They're watching the moment the universe became transparent.
That is just
Okay.
gives me chills. We are surrounded by the afterglow of the Big Bang.
We are, but then the excitement fades, the fog clears, the light passes, and the universe goes dark.
The lights go out.
Yes, there are no stars yet, no galaxies, just invisible clouds of hydrogen and helium drifting in the absolute darkness.
The cosmic dark ages.
It sounds spooky, and it was. For about 100 to 200 million years, nothing shone. It was a silent black void.
But it wasn't empty. Something was working in the dark. The architect was on the job.
The silent architect. Gravity. Gravity never sleeps. It finds those tiny lumps of matter. Remember the quantum jitters from inflation?
The wrinkles in the sheet, the slightly denser spots.
Right. Gravity starts pulling gas towards those wrinkles. A little clump gets bigger, which gives it more gravity, which pulls in more gas. It's a snowball effect, happening in slow motion over millions of years.
Until finally, the pressure gets too high in the center of these clouds.
The center of the clump gets hot, denser and hotter, until ignition. Nuclear fusion begins.
Cosmic dawn.
The first stars turn on, and the dark ages end with a blaze of glory.
Now tell me about these first stars. These are the population third stars. The notes call them the rock stars of the universe.
They were absolute monsters. These stars were likely hundreds of times more massive than our sun, maybe even 1,000 times. They were pure hydrogen and helium.
So they burn differently.
They burned incredibly hot and incredibly bright. They were blue giants, burning with a ferocity we can barely imagine.
Live fast, die young.
That's the motto. Because they were so huge, they burned through their fuel incredibly fast. They lived for maybe a few million years. Our sun will live for 10 billion. These guys were a flash in the pan.
But they had a job to do. A crucial job for the rest of the story.
A vital job. You see, the Big Bang only made hydrogen and helium. That's it. You can't build a rocky planet out of gas. You can't build a human being out of helium. You need heavier stuff.
So where did the carbon and oxygen and iron come from?
The rock stars cooked them. Inside their cores, under that insane pressure, they smashed atoms together to create heavier elements. They were the first alchemists. They turned hydrogen into carbon, into oxygen, into iron, all the way up the periodic table.
Back then, they couldn't just keep it all to themselves.
And then they exploded. Hypernovae. Explosions so powerful they seeded the cosmos. They blasted those new elements out into the void.
They polluted the universe.
Yeah.
But in a good way.
They salted the soup. They filled the universe with the periodic table. Without those first stars living and dying, chemistry would not exist. Life would not exist.
So we owe our existence to the ashes of these dead giants.
We are star stuff, quite literally. The iron in your blood was forged in the heart of a star that died billions of years ago.
That brings us to section 3. The universe is seeded with heavy elements. Galaxies are forming. Welcome to the Stelliferous era.
The age of stars. This is where we are right now. This is our time.
The prime of life. The universe is a teenager, maybe, full of energy.
Exactly. Gravity has been busy building structures. We have hundreds of billions of galaxies, each with hundreds of billions of stars. It is an era of extreme complexity in light.
The notes mention the anthropic principle regarding timing here. The idea that we are living in a golden afternoon. Why now? Why are we here 13.8 billion years in? Why not earlier?
It's a bit of a Goldilocks situation. It's not a coincidence that we find ourselves alive right now. We couldn't really exist 10 billion years ago.
Why not?
The universe was too dangerous. It was full of quasars and exploding stars. Radiation was everywhere. Plus, there hadn't been enough generations of stars to create enough iron and silicon to build stable, rocky planets. It was a construction zone.
Okay, so not too early. Why not later? Why not show up in, say, another 50 billion years?
If we waited another 100 billion years, the universe would be running out of gas. Literally. The gas needed for star formation would be mostly used up.
So the star factories would be shutting down.
They'd be slowing down for sure. The universe would be getting darker and colder and more spread out.
So we are here at the peak, the perfect moment.
Well, actually, we are a little past the peak. The absolute peak of star formation, the baby boom of the universe, was actually about 10 billion years ago.
Oh, really?
Yeah, the party was raging hardest back then. The universe was building stars at a much higher rate.
So we are the late bloomers. We showed up for the after party.
Our sun was born 4.6 billion years ago, which is on the tail end of the boom. But that's good for us. It means the universe had time to settle down. It's calm enough for life to evolve without getting fried every other Tuesday.
But this era has a villain. Or at least a plot twist we didn't see coming until very recently.
The 1990s, the discovery of dark energy. This changed everything we thought we knew about the future.
Before this, everyone thought the expansion of the universe would slow down, right? Gravity pulls things together, so eventually the expansion should break.
Exactly. It's like throwing a ball in the air. You expect gravity to slow it down. The big question was, would it slow down and stop? Or maybe even stop and fall back, the big crunch.
The universe collapses back in on itself.
Right. But that's not what happened.
No. Astronomers looked at distant supernovae to measure the speed. And they found something terrifying.
The ball isn't slowing down, it's speeding up.
It's shooting up into space faster and faster.
The expansion is accelerating. And the culprit is this mysterious energy field we call dark energy. It acts like negative pressure, pushing space apart from the inside. It's an anti-gravity force built into the fabric of space-time.
And this leads to a very lonely future, a very profound consequence.
This is one of the most sobering realizations in modern cosmology. Because the universe is expanding faster and faster, galaxies that are far away from us are being pushed away.
And eventually,
Eventually, they will be moving away from us faster than the speed of light.
which means the light from them can never reach us.
Exactly. They will slip past the cosmic horizon. They will vanish. One by one, the lights will go out.
So imagine an astronomer living on Earth, or whatever planet we are, on 100 billion years from now. What do they see when they look through their telescope?
That is the tragedy. They would look up and see nothing, just the stars of our own galaxy, which is bound together by gravity.
Our little local group might still be around.
Right, our local cluster will have merged into one supergalaxy. But beyond that, a blank black void. No other galaxies, no cosmic microwave background, no evidence of the Big Bang.
The clues will be gone. The evidence will have expanded beyond their reach.
The receipts we talked about at the beginning, they will be erased. Future civilizations will likely believe that their galaxy is the entire universe and that it is static and eternal.
Their science will be fundamentally limited. They'll have no way of knowing the grand history we are discussing today.
It makes me feel incredibly lucky. We live in the only time where the universe is transparent enough and connected enough to tell us its own story.
We have the best seat in the house.
For a very limited time.
So enjoy the view while it lasts, folks. Because now we have to turn the page to section 4, the long goodbye.
This is where things get somber. The stelliferous era cannot last forever. Stars run on fuel, hydrogen, and the universe has a limited supply.
It's not getting a refill. The tank is finite.
No. So slowly, the lights start going out. The big, bright stars die first. They've already been dying for billions of years. Then the medium ones, like our sun.
And when does our sun check out?
In about another 5 billion years. But that's just one star. We're talking about the whole cosmos now.
What's the timeline here for the end of star formation?
In about 100 trillion years, the very last star will be born. The gas will be too thin and diffused to collapse anymore. After that, no new stars. The nursery is closed for business.
And the last ones to die. The last lights to go out.
The red dwarfs, they are the efficient economy cars of the galaxy. They sip their fuel. They're very small, very cool. They can burn for trillions of years.
But not forever.
Not forever, but for a very, very long time. But eventually, even they will flicker out and become cold, dead embers.
And when the last star dies, what's left?
We enter the degenerate era.
That sounds gritty, and not in a good way.
It's an era of corpses. The universe will be a graveyard filled with the leftovers of stars, white dwarfs, which are the cores of dead suns, neutron stars, the crushed remnants of supernovae, and black holes.
And it will be dark. Utterly
And
dark.
cold. It will be dark, it will be cold, it will be mostly empty.
But not completely dead yet. The notes say something about zombie stars.
Not quite. There will be zombie stars. That's a great term for it.
Zombie stars? What on earth are those?
Occasionally in the dark, two white dwarfs, these dead star cores, might spiral into each other and collide. That would create a supernova, a brief, violent flare of light in the eternal darkness.
So there's a flash of
A
excitement.
very rare one. But those will be rare moments of excitement in a vast, silent tomb that lasts for trillions upon trillions of years.
And then even the corpses disappear. This is the proton decay theory. This one is really out there.
This is theoretical. We haven't observed it yet. The timescale is too long. But most models of physics suggest that protons, the building blocks of atoms, the stuff that makes a rock, are not stable forever. They eventually break down.
How long does that take?
The timescale is unimaginable. Around 10 to the power of 40 years. That is a 1 with 40 zeros.
I can't even, my brain just shuts off.
Right. It's just a number on a page at that point.
And if protons decay, what happens to physical objects? To those white dwarfs and neutron stars?
They dissolve. Planets, dead stars, dust, your coffee mug. If it survived that long, it would all just evaporate into subatomic radiation. The solid matter of the universe simply melts away like iced in warm water.
So there are no rocks left. No dust. What is left at the end of this era?
The kings of the dark, black holes.
The black hole era. Now they're the only game in town.
At this point, the universe is just empty, expanding space and scattered black holes. They're the only things holding on to any concentrated energy or matter.
But even they aren't immortal. We used to think they were.
No. Stephen Hawking taught us that. Black holes leak. It's called Hawking radiation. It's an incredibly slow process, a quantum effect at the edge of the event horizon. But over time, they lose mass. They evaporate.
How fast are we talking here? How long does a black hole last?
For a black hole, the mass of our sun to evaporate completely, it takes 10 to the power of 67 years.
Okay. That's already a meaningless number.
But for the big ones, the supermassive black holes at the center of galaxies, the ones that are billions of times the mass of the sun, it takes 10 to the power of 100 years.
A Google years.
A Google years. To give you a sense of that number, if you wrote a 0 on every single atom in the visible universe, you wouldn't have enough atoms to write the number down.
And during that whole time for a Google years, nothing else happens.
Pretty much nothing. Just black holes slowly spinning in the dark, leaking energy one photon at a time. It is a time scale that makes the entire history of life on Earth look like less than a heartbeat.
And then, at the end of that Google years,
Then the last black hole evaporates. It pops out of existence in a tiny puff of particles. And the universe is empty.
and that's it. That's the end. Section 5. Finale.
Heat death.
The name always confused me. It sounds violent, like burning up,
Yeah.
but it's actually the opposite, right? It's the ultimate cold.
Yes, it means the death of heat.
Mm.
Or more accurately, the death of heat differences. It is the victory of entropy.
Unpack entropy for us in this context. It's a word we hear a lot, but is often misunderstood.
Entropy is just the tendency for things to spread out in disorder. Heat flows from hot things to cold things. Once everything is the same temperature, nothing can ever happen again.
Why not?
Because you can't run an engine without a heat difference. You can't have a thought without energy flow in your brain. You need a gradient. You need order moving to disorder.
So heat death is the flat line, when the gradient is gone.
It is the ultimate stillness. Imagine a space so expanded that it is practically infinite. There is no matter. Just a few lonely photons of light and other particles stretching out across billions of light years.
And they never hit anything.
They never hit anything. They never interact. The temperature is a fraction of a fraction of a fraction of a degree above absolute zero.
Total silence.
Total stasis. There is no arrow of time anymore because nothing changes. Past, present, and future become meaningless.
That is incredibly depressing, I'm not going to lie. It feels like such a waste. All that trauma, all those stars, all of us,
Yeah.
just to end up as a cold, static hiss for eternity.
It is a bit bleak. It's the ultimate tragedy. All that structure and complexity just dissolves back into nothingness.
Is that really it? Is that the final period in the biography? Is there no encore?
Well, here is where it gets really interesting and maybe a little hopeful. There is a twist.
I was hoping for a twist. Please tell me there's a twist.
There is a physicist named Roger Penrose, a Nobel laureate. He has this theory called conformal cyclic cosmology.
That is a mouthful. Let's unpack it. Conformal cyclic cosmology.
His argument is based on what we just discussed.
Hmm.
In the heat death, there is no mass, no atoms, no protons, just photons and other massless particles.
Right. Everything is decayed or evaporated.
And relativity tells us that photons, light particles, do not experience time. From a photon's perspective, its entire journey from a star to your eye is instantaneous.
Right. Time stops at the speed of light.
And without mass, the concept of scale, how big something is, loses its meaning.
Why does scale lose meaning? That's a big jump.
Because scale is relative. You are big compared to an ant, but small compared to a mountain. If you have no atoms, no meter sticks, no clocks, there's no difference between a universe that is infinitely big and a universe that is infinitely small.
I think I'm following.
Mathematically, they look identical. An infinitely large, cold universe with no mass has the same conformal geometry as an infinitely small, hot universe with no mass.
Whoa. Wait. See that again?
So Penrose argues that the mathematical state of the universe at heat death, infinite, empty, massless, is actually the exact same mathematical state as the Big Bang.
So, the end of the universe is the beginning of another one.
It could be. The heat death of our universe becomes the inflation of the next one. The cold, empty vastness forgets how big it is, and suddenly, bang, it resets. The whole cycle begins again.
That changes everything. It means the biography isn't a single book, it's a series.
Exactly. We might be just one volume in an infinite library of universes. One eon, as he calls it, born from the ashes of the previous eon and destined to seed the next one.
I like that a lot better than the eternal frozen darkness. That feels right, somehow.
It gives a rhythm to existence, a heartbeat, expansion, emptiness, rebirth. It makes the universe feel like an organism that breathes on a timescale we can't comprehend.
So what does this all mean for us? We are standing here holding the receipts, looking at a timeline that stretches from 10 to the negative 43 seconds to 10 to the power of 100 years.
It is humbling. It reminds us that our daily worries, the traffic, the emails, the social media arguments are happening in a tiny, fleeting spark of light in a vast, dark cathedral.
We are just a blip, a momentary thought.
But it's also empowering, isn't it? I think that's the more important takeaway.
How so?
Because we are the part of the universe that woke up. We are the atoms that came together, evolved a brain, and turned around to look at the beginning and say, I see you. I know how you work.
We are the universe experiencing itself.
That's the most beautiful part. For this brief golden afternoon, the universe isn't just dark energy and hydrogen gas. It's conscious. It's wondering. It's recording its own biography through us. We are its memory.
Well, my brain is officially full. We have traveled through time, watched stars die, sat in the dark for Google years, and maybe saw a new universe get born.
Not bad for an hour's work.
I want to leave our listeners with one final thought, something to do tonight.
What's that?
Look up. Seriously, go outside tonight, find a patch of dark sky, and just look up. When you see those stars, remember that you are looking at the engines of creation that made the iron in your blood. You are looking at history. You are looking at light that has traveled for thousands or millions of years to reach you.
You're looking into the past.
And you are looking at a story that is still being written. And you're part of it.
And remember, you are the one in a billion that survived the massacre. You are the lucky one.
Thanks for diving deep with us today. This was epic.
It was a pleasure, a true journey.
We will see you on the next one. Keep looking up.